Hello, everyone. Welcome back to lesson 19 of the ACSL contest. So today's topic is going to be graph theory, which is part of contest 4 and is tested in all the divisions, including elementary division. Yeah. So to get started, let's first talk about some applications of graphs in daily life. So all of you might be familiar with this when we are using Google Maps or any similar application, and we want to look for the fastest route from point A to point B, then we are utilizing a graph. So right here, there's a picture of the fastest route from Los Angeles to Las Vegas, and there are many different routes, and we can calculate the fastest one. Another example is finding the most affordable ticket to New York. And we have the criteria that we can consider flights with up to 2 layovers. And the last one is a theory called the 6 degrees of separation, which states that all people are 6 or fewer social connections away from each other. So you can think of it as like a friend of a friend. And such a statement can be made connect any two people in a maximum of 6 steps. So in this picture over here, we can see that Brian is 6 degrees of separation from Arnold. Okay, so now you might be wondering, what is the definition of a graph? So why are we learning all of this? A graph is a nonlinear data structure that consists of nodes, which are also called vertices, and edges that are joining the vertices. So a graph is just a collection of vertices and edges, in other words. And an edge is just a connection between any two vertices. So does anyone have any questions on this? I'll get into an example in a bit. So just a recap, a data structure is used for organizing, processing, retrieving, and storing data, and a graph is a type of data structure. But unlike linear data structures such as arrays, stack, and queue, which we have previously learned, and those all have sequential arrangement of elements, graphs allow us to have more complex relationships and connections between data points. And this makes them more suitable for modeling various real-world scenarios where relationships are not necessarily sequential. So for example, in the previous slide, this friend circle right here is not necessarily a sequential relationship because people can be interrelated in many different ways. Yeah, so next slide. So here are some examples of graphs. So we have in this picture, A, B, C, and D are vertices. They're also called nodes, and they're connected by edges. And they, in this picture, we have AB, AC, BC, AD, and DB. And there's no edge between C and D. Does anyone have any questions? Okay, so I'll get into more graph terminology that you'll have to be familiar with for the ACSL contest. So typically we can call graphs with the letter G, and they, once again, they are a set of vertices, which we can sometimes call V, and edges, which we can use the letter E to represent. Edges exist between pairs of vertices, and if vertex X and Y share an edge, that means they are adjacent, or sometimes we can use the term neighbors. So for example, we can draw a simple graph here. and we can label the vertices. So A, B, and C are vertices, and this right here is an edge. An edge in an undirected graph can be traversed in either direction. That means we can go from A to B and B back to A. So if that is the case, then it is an undirected graph. And a path is a sequence of vertices that are connected by edges. So for example, A, B, C is a path. So we can have multiple vertices that are all connected by edges. The in degree of a vertex V is the number of edges with V as their endpoint. And the out degree is the number of edges with V as their starting point. So does anyone have any questions? Okay, we'll see more of this later. And a complete graph is a special kind of undirected graph, which means that there is one edge from every vertex to each of the other vertices. So basically every two vertices are interconnected. These graphs are the same thing as drawing a polygon of any number of sides and drawing all of its diagonals. So right here we have 1, 2, 3, 4, 5. It's basically like a pentagon with all the edges and diagonals drawn. So the number of edges is equal to the number of vertices plus the number of diagonals. And you can also think of it as n choose 2. So we can choose any two vertices, and the number of those combinations is the total number of edges. Okay, next we have a simple path, which is a path between two vertices in a graph. And yeah, so a path between two vertices in a graph is a list of vertices in which successive vertices are connected by edges in the graph. So for example, AB is a path of length 1, while ABC is a path of length 2 from vertex A to vertex C. So in the diagram, this AB is just a path of length 1, while ABC is a path of length 2. And a simple path is a special type of path where no vertex is repeated. So in this case, BACBD is a path of length 4, but it's not a simple path because B is repeated twice. However, BD and BAD are considered simple paths. So next we have connected graphs, which are, and a graph is connected if there's a path from every vertex to every other vertex in the graph. And connected components refer to a subgraph in which every pair of vertices is connected by a graph. So in simpler terms, all vertices within a connected component are reachable from each other. So this first picture right here is a connected graph because from any vertex, we can get to every other vertex. But this one over here on the right, it is not a connected graph because the 0 vertex is unable to reach any of the other vertices. But however, in this picture, there are two connected components. So 0 on its own is a connected component, and the rest of the nodes are also connected components. So connected components are subgraphs. Does this make sense? Okay. So next we have a cycle, which is a path that is simple except the first and last vertex is the same. So it's basically like what it sounds like. It's a cycle, so it's a path from a point back to itself. Yeah, so what's a subgraph? That's a good question. A subgraph is basically like a graph inside of another graph. Yeah, so for example, so we're talking about cycles. So for example, ABDA is a cycle because we start from A and then we go back to A. And the vertices can be listed in the order they are traveled, but actually any of the vertices can be listed first. So for example, we have A, B, C, D, A, B, D, A. So we are talking about this cycle right here. So this can be written as A, B, D, A, but it's also the same thing as B, D, A, B. So we can trace it in many different ways, but they are essentially the same thing. So there's many different ways to identify the same cycle. But depending on the context, we may list, we can choose to list which vertices first. Okay, so here is a quick question. In an undirected graph, is ABA a graph with a cycle? So what do you guys think? I know the answer is there. So ABA is not considered a cycle because cycles have to have 3 or more vertices. So ABA basically, you're basically like retracing the same path. Yeah, so what is an undirected graph? Let me go back to the slide. An undirected graph is basically a graph that can be traversed in either direction, which means we can go from A to B, and we can also go from B to A. So it's like both ways. Does that make sense? Yeah. Yeah, so a simple edge of the graph cannot be considered a cycle. So ABA is basically just an edge. It has to have 3 or more vertices in order to be considered a cycle. And another observation is that there's always an even number of cycles in an undirected graph. For example, over here, ABDA and ADBA is like a pair. So we can go forwards and backwards. And then, so that's these two. ABCA and ACBA are the same. And then we have a more complicated one, ACBDA and ADBCA are also the same. They're the same except they're in 2 different directions. So in conclusion, there's always an even number of cycles. And now, so contrary to an undirected graph, there's also directed graphs, which are graphs that have direction associated with each edge. So an edge x, y in a directed graph can be used in a path that goes from x to y, but not necessarily from y to x. So when we write the edge, we can list them in the order from like the origin to the destination. But if it's a directed graph, it's not necessarily both ways. And we can use arrows to represent the direction. So C to F, we can go both ways. But for example, the connection between A and B, we can only go from A to B. So this is a directed graph because we have direction associated with the edges. Next, we have graphs. with no cycles that are known as a tree. So there's only one path between any two nodes in a tree. A tree with n vertices contains exactly n minus 1 edges. So for example, the graph on the left here, we can't form any cycles. And so between any two nodes, for example, this one and this one, there's only one connection. There's only one path. And this tree has 4 different vertices, and there are 4 minus 1, so there are 3 edges. And a group of disconnected trees is called a forest. So if we're talking about both of these graphs, this is a forest. This one is also a tree. So basically many trees consists of a forest. Does anyone have any questions? If not, then we'll move on. Next, I'm going to introduce the concept of a weighted graph, which is a graph that has a weight to it, also referred to as a cost, that is associated with each edge. Let's see if I can clear the annotations. Yeah, so weights can be the distance between two vertices, or time, or flow, if we're referring to traffic flow or water flow, price, etc. So it can basically be anything that is associated the with the edge. So if we have a graph that looks like this, we can like basically associate numbers with them. It could be the price or the time or the distance. So if we're talking about different cities, like cities A, B, and C, I'll draw this to scale more. In this case, the weight is referring to like the distance. So weights are associated with edges. Okay. Now I'm going to introduce the traveling salesman problem, which basically goes as this. Find the best route for a salesperson to take if he or she wants to reach every stop or vertex once and only once while starting and ending at the same place. So basically, if we're talking about like delivering, like Amazon delivering, and we want to deliver goods to every single house or every stop, and we're only going to each place once, and we're going to start at and end at the same place. Yeah, so this is a very difficult problem in today's world. And so we can start with, let's say there's 10 cities, numbered 1 to 10, and we're going to start from 1 and end at 1. So to make it more simple, let's just say there's 5 cities, and we're going to start from this one. So how can we calculate the number of paths to take to deliver goods to every single house and then go back to the origin? So for the first choice, so yeah, that was just to demonstrate, but now let's go back to saying there's 10 cities. So for the first city, we have 9 different options. So if there's 10 cities and we're currently at city 1, we can go to city 2, 3, 4, 5, 6, 7, 8, or 9. So there are 9 options. And then how many options for the second city? We have 8 options. So basically the total number of possibilities, yes, Roger said it, is going to be n minus 1 factorial. So that's a lot of different options. And in this case, we only have 10 cities, but what about if there are 100 cities? It's going to be very hard to solve this. So this is a very well-known NP problem, which stands for non-deterministic polynomial time. So basically, this problem can't be solved using a polynomial since we're dealing with factorials. Does anyone have any questions? Okay, then let's move on. We also have a concept called a traversable graph. The traversability of a graph refers to whether or not you can use every edge once and only once without lifting your pencil, basically. And a famous example of this is the 7 bridges of Königsberg. So just some background about this problem. The city of Königsberg in Prussia was set on both sides of the Pregel River and included 2 large islands which are connected to each other and the mainland by 7 bridges. Yeah, so these are the 2 islands, and there are 7 bridges connecting the islands to each other and to the mainland. And the problem here is to devise a way to walk through the city that would cross each bridge once and only once. So we want to cross each bridge, but we can only cross each bridge once. And with the conditions that the islands could only be reached by the bridges, so the only way we can go to the islands is via the bridges, and every bridge once accessed must be crossed to the other end. So you can't like cross halfway and then go back. That is not allowed. The starting and ending points of the walk need not be the same. So take a moment to think about how we can cross this, how we can satisfy this problem. Okay, Roger says there is no possibility. So why is that? So take another moment to think about this problem. You can even draw it out. Because you're bound to hit the same island slash mainland eventually. Yes, but why is that? If there's no possibility, then it's given that you're going to go back to you're going to cross the same path. Okay, so I'm going to talk about the solution to this problem. It was first solved in 1735 by Leonhard Euler, and he's basically solved the problem by identifying each vertex as having a degree. And the degree represents the number of edges that came into that vertex. So for example, And also, by the way, this is the original diagram of the city, but we can simplify it into a graph. These are equivalent. So vertex A has degree 3 because there are 3 edges that go into vertex A. And vertex B also has degree 3. RSV are the paths that lead to vertex B. Vertex C has degree 5, and vertex D has degree 3. And Euler concluded that the number of vertices of odd degree must be either 0 or 2 for a graph to be traversable. Basically, what he was saying is that, let's say this is an island. You have to walk into the island, but you also have to walk out. So it has to have an even number of vertices, except the first starting point and the destination. So that's why you have to have either 0 or 2 number of odd vertices with odd degree in order for this to work. So now I'm going to play a video explaining this. Can you guys hear the sound? Share computers. Let me see. Okay. Now,
You'd have a hard time finding Königsberg on any modern maps, but one particular quirk in its geography has made it one of the most famous cities in mathematics. The medieval German city lay on both sides of the Pregel River. At the center were 2 large islands. The 2 islands were connected to each other and to the riverbanks by 7 bridges. Carl Gottlieb Euler, a mathematician who later became the mayor of a nearby town, grew obsessed with these islands and bridges. He kept coming back to a single question: which route would allow someone to cross all 7 bridges without crossing any of them more than once? Think about it for a moment. Give up? You should. It's not possible. But attempting to explain why led famous mathematician Leonhard Euler to invent a new field of mathematics. Carl wrote to Euler for help with the problem. Euler first dismissed the question as having nothing to do with math, but the more he wrestled with it, the more it seemed there might be something there after all. The answer he came up with had to do with a type of geometry that did not quite exist yet, what he called the geometry of position, now known as graph theory. Euler's first insight was that the route taken between entering an island or a riverbank and leaving it didn't actually matter. Thus, the map could be simplified, with each of the 4 landmasses represented as a single point, what we now call a node, with lines or edges between them to represent the bridges. And this simplified graph allows us to easily count the degrees of each node. That's the number of bridges each landmass touches. Why do the degrees matter? Well, according to the rules of the challenge, once travelers arrive onto a landmass by one bridge, they would have to leave it via a different bridge. In other words, the bridges leading to and from each node on any route must occur in distinct pairs, meaning that the number of bridges touching each landmass visited must be even. The only possible exceptions would be the locations of the beginning and end of the walk. Looking at the graph, it becomes apparent that all 4 nodes have an odd degree. So no matter which path is chosen, at some point, a bridge will have to be crossed twice. Euler used this proof to formulate a general theory that applies to all graphs with two or more nodes. A Eulerian path that visits each edge only once is only possible in one of two scenarios. The first is when there are exactly two nodes of odd degree, meaning all the rest are even. There, the starting point is one of the odd nodes, and the endpoint is the other. The second is when all the nodes are of even degree. Then, the Eulerian path will start and stop in the same location, which also makes it something called a Eulerian circuit. So how might you create a Eulerian path in Königsberg? It's simple. Just remove any one bridge. And it turns out, history created a Eulerian path of its own. During World War II, the Soviet Air Force destroyed two of the city's bridges, making a Eulerian path easily possible. Though, to be fair, that probably wasn't their intention. These bombings pretty much wiped Königsberg off the map, and it was later rebuilt as the Russian city of Kaliningrad. So while Königsberg and her 7 bridges may not be around anymore, they will be remembered throughout history by this seemingly trivial riddle which led to the emergence of a whole new field of mathematics.
That is some interesting history behind these bridges, but in today's lesson, it's relevant to graph theory. So adjacent matrices are another way of representing a graph. And to draw an adjacency matrix, we can create an n by n grid and label the rows and columns for each vertex. So on the left here, we have a diagram of the graph. And then we made a 4 by 4 grid since there are 4 vertices. And we labeled the rows and the columns with the vertices. Then we can place 1 for each edge in the cell whose row and column correspond to the starting and ending vertices of the edge. So since A can go to B, at the intersection of A and B, we put a 1, which means there is a path. And A to D also has a path, so that's why there's a 1 here. And B to D has a path. So this on the left is the start, and the ones on the top are the end. So basically, we can construct such a matrix, and we fill in the rest of them with zeros, which show that there is no path between the two vertices. And we can also write the weights there in the matrix. So this is helpful because in a directed graph, we can go from like A to B, but maybe not from B to A, and we can indicate that with an adjacency matrix. So we're given here a adjacency matrix, and so I have some questions for all of you. How would you count the number of vertices? The number of 1? The number of ones, that's the answer to the next question. The number of edges divided by 2, but yeah, so size. The size of the matrix is the number of vertices. So we can look at the top or the side. They should be the same since it's an n by n matrix. So in this case, there are 13 vertices. And this also corresponds to, this is the graph and this is the matrix, so they're the same. Yeah, so the size of the matrix is the number of vertices. What about the number of edges? So Roger already hinted at this one earlier. So the number of edges is the number of ones because the number of ones divided by 2. Yeah, since this is a 2-dimensional matrix. So a 1 indicates there is an edge two between two vertices, but we have to divide it by 2 since it's an undirected graph. Yeah, we are overcounting since, yeah. So for the purposes of this, it's not too important exactly what the number is, but we're just going over the methodology. But if it's a directed graph, then there's no need to divide by 2. How about the next one? What should we do to add a new vertex to this matrix? Let's say we want to add vertex 13. Yeah, exactly. We just add a row and column. So it doesn't matter what any of this is. Yeah, increasing the size. How about adding a new edge? Don't overthink this one. Yeah, just change a 0 to a 1. That's how we create a new edge. What about getting all the neighbors? So a neighbor is basically a vertex that has a connection to the one. Yeah, so for example, 7 and 8 are neighbors, 9 and 10 are neighbors. Yeah, so basically we can just look at one column or one row. So if we're considering 0, and if we're considering all the outgoing neighbors, we can just look at here. And wherever there is a 1, there is a neighbor. So in this case, 0 is neighbors with 1, 2, 5, 6. And those are just the outgoing neighbors. But for the incoming neighbors, we can look here. So in this case, 1, 2, 5, 6. It's the same since it's an undirected graph. So if we look at the graph, we can see indeed 1, 2, 5, 6 are the neighbors. So we can just look at the row or the column, and anything that has a 1 is a neighbor. Now, what if we want to know if vertices U and V are connected? Yeah, so basically we can check the matrix UV, and if there's a 1 there, that means there is a path. If there's a 0 there, then there's no path, so they're not connected. And if it's a directed graph, if either UV or VU has a 1 in it, then they are connected. What if we want to reverse all the edges? Basically meaning if there is no connection, let's build a connection. If there's a connection, let's remove the connection. Yeah, so we can basically inverse the matrix. If there's a 0 there, change it to a 1. If there's a 1 there, change it to a 0. That way, we will reverse all the edges. And the last one, which is get two-hop neighbors. Two-hop neighbors are basically all the vertices that can be reached with a path of length 2. So for example, 4 and 0 are two-hop neighbors since we can connect them with a path length of 2. How should we do this? So this one's a bit more complicated, but basically to explain what a two-hop neighbor is again, there are two paths of length 2 from A to C. So from A to C, we can take A to D to C or A to B to C. Both of these work. And there is exactly one path of length 2 from A to D. So that would be A to B to D. That is length 2. A to D is only length 1. And exactly one path of length 2 from B to B. We can do B to C back to B. And if we want to find all the two-hop neighbors, then we can square the matrix. Yeah, so let me show how to square a matrix. Get more space. Okay, so let's first construct the adjacency matrix for this. So it was on the previous slide, this one. So it would be 0. The diagonals are all going to be 0 because you can't go to yourself. And then A to B, there is a connection. A to C, there is no connection. And from A to D, there is a connection. From B to A, there is no connection because it's a one-way path. From B to C, there is a connection. From B to D, we also have a connection. From C to A, there is no connection. From C to B, there is. From C to D, there is not, since it's one way. From D to A, there's no path. From D to B, there is also no path since it's one way. And from D to C, there is. So if we're going to square the matrix, let's just call the matrix M. M squared is the same thing as M times M. So the easiest way to do this is to just write out the matrix again, which will help when we're squaring it. So I'm going to copy it over. Okay, now this is the tricky part. So how do we square the matrix? So the resulting matrix is going to be 4 by 4, just like the starting matrix. And so first we can look at the first row of the first matrix and the first column of the second matrix. And so basically we're going to go this way and we're going to go this way. And we're going to multiply each pair and add the 4 results up, and that's going to give us the result over here. So basically 0 times 0 is 0. 1 times 0 is 0. 0 times 0 is 0. 1 times 0 is 0. So they're all 0. So we add up all the zeros. It's going to be 0. So this is just 0. And next, we're going to go to the second column. So, oops. Yeah, this is going to get messy. I'm going to use a different color. How do I change the color? Okay, so now we're going to look at this column and this row and this column. So 0 times 1 is 0. 1 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. So we have all zeros again. So this is going to be 0. Now let's look at this column over here. So 0 times 0 is 0. 1 times 1 is 1. So we have a 1. 0 times 0 is 0. 1 times 1 is 1. So we have a total of 2 1s. So this one over here is going to be 2, since we have 1 plus 1 is 2. Okay, and now let's look at this final column. 0 times 1 is 0. 1 times 1 is 1. 0 times 0 is 0. 1 times 0 is 0. So we have, if we add it all up, it's 1. Okay, so let's move to the second row, first column. Oops. So right away, I see that all of these are 0, so it doesn't matter what you multiply 0 by, the result's going to be 0, so you kind of don't have to do it really. And then now we're going to look at the second column. So 0 times 1 is 0, 0 times 0 is 0, 1 times 1 is 1, 1 times 0 is 0. So when we add it all up, we get 1. And then the third column, 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is, wait, 1 times 1 is 1. Yeah, so we have 1, 1. And then I'm not going to do the rest. You can go through all the multiplication, but this is basically how you multiply two matrices together. But the result is here. So basically what this shows, there's no way to do it quicker. You can use a calculator. Some calculators support matrix multiplication, but that is not allowed in the contest. So you have to do it manually. Basically, you just go from left to right and then go down, and you can use your fingers and basically like do this. Um, how can we do this? And so FSA is contest 3. This is contest 4. So luckily they're not in the same contest. But it's not as hard as you think, and it's actually pretty fast if you practice this. But because you're just multiplying zeros and ones, and that's all there is to it. Yeah, so Um, but this is only because it's graph theory, but um, for other matrices, you could be multiplying bigger numbers, so it would be a lot more complicated. But it's only zeros and ones since we're indicating if there is a path. Yeah, and this is a concept that you'll learn in higher level algebra. But basically what the result shows, what M squared shows is that there are two paths from A to C. There are two paths of length 2, specifically from A to C. So that is A, okay, I can erase this now. That's A to D to C and A to B to C. And there is one path of length 2 from B to B. That is B to D back to B. There is one path of length 2 from B to C, which is B to D to C. So that's basically what this resulting matrix shows. And if we want to find 3 hop neighbors, we can do M cubed. And for 4 hop neighbors, that's M to the power 4, etc. So that's a reason why adjacency matrices are super helpful, because we can do operations with them to find the number of different paths of different lengths. So why can we not do B to C? What do you mean? Oh, okay, I see. There is no way from B to C in 2 jumps exactly. Okay, so that is how to get 2 hop neighbors. It's sorry, what is did I answer your question? Okay, then why do why do you have to do B to D to C? Yeah, so to get from B to C with a path length of 2, we have to go to D, and then from D go to C. We can go from B to C directly, but we're finding um, only connections of length 2. Does that make sense? Okay, then let's move on. Okay, so let's take a moment to do this problem. Find the number of different cycles contained in the directed graph with vertices A, B, C, D, E, and edges A, B, B, A, B, C, C, D, D, C, D, B, D, E. Yeah, so I will go over the solution. Okay, so let's first draw out what the graph looks like. So we have A, B, and then C, D, E. And then we have the edges AB, BA, BC, CD, DC, so both ways, DB, and DE. Okay, and then we're looking for the number of different cycles. Okay, so BC, let me use a different color. BCDB is a cycle. ABA is a cycle. And CDC is a cycle. So I think the answer for this one should be 3. Does that make sense? Okay, then that is going to be the end of today's lesson. So yeah, thank you all for coming.
Thank you.
Thank you.
Yeah.
Bye.
Thank you. Bye.
Thank you.
Thank you. And yeah, AB is not a cycle since we have to go back to where we started.